Hello and welcome back to Calculus 1 section 5.5 U-sub. So the deal is you learn U-sub and you have a chance of surviving Calc 2 and beyond. Skip U-sub and your education with calculus ends with Calc 1. So U-substitution is the most frequent integration technique, and most of techniques that you learn in Calc 2 will be the methods and manipulations to get your integral to the form where you can use U-sub. So this will be, you know, like in Mortal Kombat you have the finishing screen, right? That's gonna be that, all right? So this finishes up every problem pretty much in Calc 2. A lot of integrals will depend on U-sub. Now you might ask yourself why? Why is it such a big deal? We did basic integration. That should be the most frequent. Well, remember your derivatives. Are basic derivatives most frequent problems you see? The answer is no. You are going to see sine 2x, sine 3x, sine x squared, sine of composition of functions. That is the most frequent derivative you take, and that is chain rule. This guy, U-sub, is backwards chain rule. Therefore, it must inhabit that property of being the most frequent integration technique. And you have to master this one to go on in the field of math. You have to learn this. Now, a lot of this is going to be dependent on your ability to see what I call function derivative pairs. So yes, this is integration technique, but knowing derivatives here is absolutely essential. So I'm going to write down 3 problems. So one problem looks like this. It is e to the x dx, and we know that's basic, right? And then you have e to the x squared dx, which is, I'll just say hell no. And then we have integral x e to the x squared dx, which is going to be U-sub. So the differences between problems are subtle, right? Now, when I discuss these 3 problems, the first one is basic. You know this from your section 4.9. You know that the answer to the first question is itself e to the x plus c, and you're done. The second problem where I said hell no, we added a square on x. So you might say, it's not that much different, right? But it turns out that you can't compute this by any methods that you learn here, right? And there are some methods that you can employ from Calc 2, and then a really crazy thing from Calc 3 that we never actually do. But when I say hell no, it's hell no. There's no integration that you can pull off as a Calc 1 student to do anything close to solving that one. But then you have this one, and this is what we are learning today. So going from hell no into yeah, we can do it, right, is oh, I just added an x in front, right? Now, I already mentioned that the ability to do this section, which is one of the most important techniques of integration, is going to lie within your ability to spot function derivative pairs. Now, you see x squared, and you know its derivative is 2x. You don't quite have 2x, but it's close enough. So there is a function derivative pair present in the last problem, and we can use U-sub. There is actually a function derivative pair present in the first one as well. What's the derivative of x? 1, right? So those problems are easily solvable. Anytime you have a function derivative pair present and you can work with that, sure. What is the function derivative pair here? Yeah, exactly. The derivative of x squared is 2x, not there, right? And we can't fix that. So, L1, right? Now, before I go into function derivative pair and solving these types of problems, I'm going to start working with polynomials because that would be the easiest thing to consider. So I want to start with simply integral of x squared dx is x cubed over 3 plus c. We know this from 4.9. I'm going to now boost the power, so we're going to go to x to the 8 dx, and we are going to get x to the 9 over 9 plus c. Now, what I'm going to do is I'm going to change this x into x plus 7 squared dx. Now you know how to solve this. You can FOIL, right? You can FOIL, you can get that good old x squared plus 14x plus 49 dx, and then integrate. You get x cubed over 3 plus 7x squared plus 49x plus c. But hell breaks loose with x plus 7 to the 8th power dx. Right? What used to be a jump that is, yep, not a problem, all of a sudden to FOIL with the 8th exponent is a living nightmare. But then you realize that this problem here and this problem here are essentially looking the same. Except that one up there has an x and we get the answer over there. The one on the bottom has x plus 7. And this is where U-substitution comes in handy. If you adopt the way of thinking, which, you talk to yourself as you're doing this problem. You say, I could do this problem if this x plus 7 was a variable, rather than x plus 7 expression. If that was a single variable, I can do the problem. But then you have to fit everything else, because now you are changing variable x to u. Your dx has to change into du. The dx is not there for decoration. It has a variable x, and you remember that's the width of your rectangle. So you cannot change the height of the rectangle, which was in terms of, right, it was f of x, and now you want to change that into some different function g of u. You can't leave your delta x, which was dx, in terms of x. That has to change into du. So, as you are dealing with the U-substitution, your job is to, and here it is written in blood, change all x's into u's. This includes dx with 3 exclamation points after that. So rewrite the problem. Integral of x plus 7 to the 8 dx, and I said in my head, I know I can deal with this problem if this x plus 7 was a single variable, and I'm going to call it u. Well, now, to find the relationship between dx and du, I can simply take the derivative of this in respect to x. So, du dx is equal to 1. Move dx to the other side, and you get du equals dx. So it's a clean swap, right? So now my problem transformed becomes the integral. Instead of x plus 7, I have u. We have to keep the 8th power, and dx is equal to du. So there is the problem. Now this is easy. U to the 9 plus c. Right? Solve it like that, because it's just a basic polynomial. which we know how to solve from our good old 4.9. Whether you're integrating u to the 8 or x to the 8 du, doesn't matter, right? So we know how to solve this. So what I have done is I took something that I don't know how to deal with, said in my head, if I can just make that a single thing, then I can deal with it, differentiated that expression to come up with a relationship between dx and du, because dx has to change into u as well. All of the variables have to change. And came up with the integral that it's easy to solve. But now we have the final problem. The solution cannot stay in terms of variable u. It has to go back to x. This is where you can use the sentence, I don't care about u, I care about the x. Yeah, you have to use that responsibly. It's not always applicable. I mean, it might be applicable, but... So, I'm going to put 1/9 in front, and instead of u, I have x plus 7, which is raised to the 9th power, and I have plus c. And that will end the problem. Now, if you are wondering whether this is correct, you will quickly take the derivative like any other problem you did so far, where you are, if you are interested. And you see that you have to use the chain rule, oops, where's my plus c, to solve this. So you have 1/9 times 9x plus 7 to the 8 plus derivative of c is 0. And then these guys cancel. The whole thing is x plus 7 to the 8, which is where we started. So no questions asked that it's correct. It is correct, right? Because we did the check. Now, if you do the check for U-sub and you don't have to do chain rule, clearly the problem is wrong. Because U-sub is backwards chain rule. Here, in blood. U-sub is backwards chain rule. When you go to Calculus 2 and you take chapter 7, 7.2 is going to be integration by parts. That's backwards product rule. So you are going to learn more powerful techniques. That one is more powerful than this, but this one is still number one because you have more chain rules than product rules to work with. So U-sub is backwards chain rule. We can finally discuss, yes?
So that blue text you did,
that's the U-sub, yes.
That is, you need to write that. You can't just
wing it. No.
Wing it? Okay.
This is the core. The blue is the core. And that's going to change for every problem. There is no prescription there. There's just experience. How many problems you did? Have you seen every situation? Sometimes, well, you'll see all of the, because I'm about to do 50,000 problems in this.
Now, if you were to write that in like a...
In green, it will be still the same.
No, but like in like the terms of like, you know how we write the theorems and such? What would it be like? U equals f of x to...
Procedure. Procedure, procedure, procedure. You remember how you had to memorize the formula? E to the ax dx is equal to EAX over A plus C, right? And you had the same thing for sine and cosine when this A was divided. Well, we can actually do the problem, let's say e to the 3x dx. We can do the problem now. And you can use U-sub clearly. You can go and say, I can do this problem if it is e to the single variable. You always have to start there. What is the overall shape, the overall look of the integral, and what you could do if the world was better, right? So you say u equals 3x, because that is going to create integral e to the u, right? That's what's going to do for us. So that's why I want to remove the 3x and put a single variable instead, so that I can get situations that I can integrate like this. That's the goal of the whole thing. But now, there's never free lunch, right? You have to differentiate this thing to get the relationship between dx and du. So now as you differentiate this, you get the du over dx is equal to 3, from where du is equal to 3 dx. That's the trouble right there. You don't have 3 dx. So you have two options. You can either put in a 3 and a 1/3 to balance it, or what is favorable for some students is to solve for dx as du over 3. So let's use that one for now. So now that this 1/3 goes in front of the integral, and I'm left with e to the u du, which is 1/3 e to the u plus c. I don't care about u, I care about the x. There we go. And problem solved. You got your e to the ax over a. Now, you know, this 3 could be 5, could be 17, could be pi, whatever else. So we see that the formula that you had to memorize now is something that you can compute using basic U sub. Now I want to address this, this thing here that I said there is another way to deal with this. And you are only able to fix these issues if you are off by a constant. If you're off by a variable, you can't. So let's prove that the integral of cosine ax dx is equal to sine ax over a plus c, using the same ideas. But I'm going to do it differently now. I'm not going to solve this. I'm going to actually fix the constant within. So let's say you want to integrate cosine of, what is a? A is 3. Again?
My go-to number.
Then let's change the person. What is your go-to number? So do we have someone who 3 is not the go-to? Anyway, yes? Oh, okay, see? All right. So you are looking at this problem. Now, if you are to just use the formula, you populate that a equals 2, top and the bottom, and you're done, right? But can we do this? And the answer is yes. Again, the way we think is you say, I know what the cosine of x, integral of cosine of x. So let me put this as a single variable so I can do that integral easily. So u equals 2x, and now it becomes cosine, right? But then again, no free lunch, right? We take the derivative in respect to x, and we get that the du dx is equal to 2, from where du is equal to 2 dx. So now, instead of solving for dx and plugging in, you see that you need 2 dx. So you know what I'm going to do? I'm going to fix it. I'm going to put 2, and I'm going to balance it in front like that. Because 1/2 times 2 is 1. I hope you see that I could have done that with the 3's earlier. Put 1/3 in front and then 3. The 3 will be absorbed by du, and 1/3 stays, which was in the answer. So now, if you are using this method of fixing, then you have 1/2 integral. Now you have a cosine of u, and 2 together with dx is the du. So that's another way of doing the same thing. You will pick your favorite and you will stick with it. What's the integral of cosine u? Sine u plus c. It's opposite than derivatives. Derivative of cosine is negative sine. Integral of cosine is positive sine. So, and then again, I don't care about u, care about the x. So that's sine 2x plus c. Cell phone for the person that cleans the offices. I was so hoping there was a security phone outside. I was so picky, I have no idea.
Nothing good comes out of randomly ringing phones.
On my end, it does.
Yeah, until the other guy's like, I'm a sniper and I'm looking right at you. Like that one movie where he picked up the
phone booth?
The phone booth.
Yeah. I've seen
that.
His
day got real bad real quick.
But there was, yeah. There are so many things. Just pick up the phone. 911 emergency, how can I help? Every time there is an unknown phone call on my phone. Every single time. It's priceless. Should try that. You don't recognize the phone as numbers calling you? Do that. Tons of fun.
Yeah, but aren't most of those just spam calls trying to get you to say yes?
You would be amazed.
So whenever I pick them up, it's a robot just trying to get me to say the word yes, because that's the scam. They try to get you to say yes so they can fake you into a verbal contract.
Yeah. They have amazing, some amazing things happen. But the wrong numbers are the best. All right. Next problem. We have unlimited supply of this. So we are ready to venture into the realm of e to the x squared dx. Right? At some point as a student, I also asked myself, what is the thing that I don't like within the problem, right? Just trying to be honest with yourself, right? What is the thing that bothers me, right? This x in front doesn't really bother me, but this exponent really bothers me, right? Because that's a function composition. Somehow this x in front, it's like a function times function. So you would say that, it's not that difficult to deal with the stuff, right? But then when you see that e to the x is a function, then x squared plugged into it, so that creates this whole new dimension of things. In some cases, I ask myself, what is that I don't like about the whole problem? And in this case was that x squared. So let me try removing x squared by replacing it with u. So a single variable u. And then the derivative over here, right, in respect to x, is du dx is equal to 2x. And then we say that the du is equal to 2x dx. Right, when you move dx to the other, you're creating essentially differential, which we covered. So now, let's compare what we have, what we need. We see that this, there's an integral, right? We see that e to the x squared is going to be e to the u, no doubt about it. Now I see the string of x dx and I have x dx. That's good. But I'm missing a 2. So I'm going to fix that. I'm going to put the 2 in front and 1/2 outside. And look at my string now. The green string over here, 2x dx is 2x dx. All of that gets replaced by du, but I gain the 1/2 in front. Are we following the colors? It's going to take some time to get used to all of these things, but...
Because right now it just seems a little arbitrary.
Yeah, multiplied by 1.
Yeah, this is multiplied by 1 because I need the 2.
So you can just like put it
you can move 2 to the other side. Yeah, there are a lot of ways. So now the integral of e to the u is e to the u plus c. I don't care about u, care about the x, so there we go. Done. I never said this is easy. All I said is the Calc2 is much worse. So yeah, we start here and you are going to use this a lot. You really have to learn this. Yeah.
Is this like write out the steps that you do that would work for the problem?
Well, the step is to figure out the part that you don't like, and I'm going to talk about it now in a different light, right? I said, oh, let me think if this was this way, it would be easy. Then I went with, oh, I really don't like this part, let me replace that, and it worked out. One thing to know is that if you make the wrong choice, your integral that you get is going to be worse than when you started, right? And in life, I hope you have that skill that if you're making things worse, stop, right? And do something else. So I hope that's the right attitude in life you have. So let's see more examples. I mean, that's all it is. So integral of e to the x cosine of e to the x dx. I'm going to ask you what you should focus on in this problem. Like which function, we clearly see e to the x, we see cosine x, right? Which one you should focus on to make stuff easy? In which respect? Yes?
Cosine of the x because if you take the derivative,
Nice. Yes. You have to focus on cosine. Cosine is the main function that floats around. And then this e to the x, it has its derivative floating about. So, see, cosine has nothing to match. So cosine has to survive in our u sub part. And this e to the x has another accompanying e to the x somewhere, so we can deal with that. Now, this is when I said work with function derivative pairs. Look, if this was x squared, then this should be an x. All right? If this was if this was ln x, which you can have cosine of ln x, then this better be 1 over x. The function derivative pair has to exist where the derivative must be the part of your du eventually. It takes time to get to the point where it works quickly, but you will notice that whatever function doesn't have its derivative pair, that's the one that survives in the overall integral that you get after the substitution is done. And if you look at all the previous problems, you will see that that exponent of 8 survived, because there was no exponent of 7 to deal with it. You will also see that e to the x, right, survived, and then cosine and so on. So being able to detect function derivative pair is essential. And here's your function e to the x, and here's its derivative, also e to the x. But this problem could be the same if I had cosine of x squared, which case I'm requiring x here, cosine of ln, which means I need 1 over x, and whatever you put here, its derivative needs to be in front for this method to work. So I'm, engineering these examples by simply starting at whatever function I want to pick in the galaxy, and then whatever function I put within that function, I need its derivative on the side.
Wouldn't the derivative of x squared be 2x?
Yeah, but we can fix those. We can fix the constants, right, by multiplying by a number in and out. What we can't fix is if you're missing x. So I can't put e to the x here and put x there, because that would not work, right? So they have to match as a function derivative pairs. So now from here I would say I can deal with the cosine x, which is cosine u. So I am eliminating e to the x. Du would be e to the x dx. If you skip a step of writing du over dx and moving dx, you can immediately write dx on the right. And look, I have integral cosine u, and then here's the green. This and this together is this, which is du. I find it that your worst enemy is this du part, because you are still resistant to accept dx as a part of the integral, which it is. It is actually dx is a half of your integral, regardless of what's here, because what I circled is a height, and this is the width in your multiplication. So you can't say that the area of the rectangle is a. It has to be a times b, and that times b is times dx. It's not there for decoration. And because it's overseen so much, generally your du portion is the one that makes a lot of problems. Integral of cosine u is sine u plus c, and then sine e to the x plus c. Yes.
The e to the x on the derivative e to the x does not match the one that's in the parentheses. So if instead of
That's the one. This is the one.
no, but what if it is cosine e to the x times x instead of e to the
Oh, no.
then
You have to have its matching partner.
that's
That's why I say function derivative pair. Function derivative pair. So function derivative pair. Integral. Don't write this yet. I have to. F of g of x dx g prime of x. Would be the antiderivative of g of x plus c. This is like a formula, but it really doesn't help other than the function derivative pair. So
Can you use these functions to substitute formula?
what happened?
Can you use this formula to figure out the other, is it okay, the other functions like Like U
Yeah, but see, this is the trick over here, to realize which function does not have a pair. That's the one that survives in the integral later on. Whatever you want.
Okay, so I can use it.
Yeah. What I am concerned about is that you have the correct answer, like 6 at the end, and that's it. Integral of sine to the 9x times cosine x dx. What would be the function that doesn't have its derivative pair, which has to be preserved and stay in the u sub integral? Which function is the one that stays? How many functions do we see there? 3. Which is the function that doesn't have its derivative pair, therefore that is the function that will stay in the u sub integral? X to the 9. Do you see any x to the 8s anywhere? You don't. So we see 3 functions. We see sine, we see cosine, and we see x to the 9. Sine and cosines are derivatives of each other. That's the function derivative pair. That's what the u is going to operate on, the substitution. The one function that doesn't have its pair there is x to the 9, in which sine is plugged in. So my u has to be sine x, because that creates u to the 9. So u equals sine x, du equals derivative of sine is cosine, so cosine x dx. And now sine x is u, so u to the 9, and the entire thing here du. U to the 10, that's 110. U to the 10 over 10 plus c equals to 1/10 sine to the 10x plus c. Meditate on this example, because I have another one coming up that it's going to wake up different emotions in you. This is where you learn u sub, with the problems that are similar but different to give you different stuff, right? So we still see sine x, we still see x to the 8, like in the previous one. Now we don't have a cosine. So try this one on your own for a few seconds until I discuss myself.
Is it actually sticking or?
Yeah. They said 2 to 4 inches.
Right.
I mean, I've been tires, so I also have to have road to do it. It's going to be that long.
Got the what button on the table?
I'm going to double that today.
Wait, how long have you been driving? I've been driving for 8 years, and I've only been in 2.
Never been. Only once it was in the snow and I wasn't even driving in the car with
Or John.
my friend. And we were
Oh,
going,
that doesn't count.
Yeah, it doesn't count for you.
yeah. But I was in the accident and I freaked out. So I'll probably be driving like 5 miles per hour.
Oh, you want to go.
Yeah. Oh yeah. Definitely.
And by the time you probably don't get tank. You can actually buy a full military tank and talk, you know, a real tank with the gun and stuff like 20,000. Look it up online. So you can. The only problem is that they don't run miles per gallon; they run gallons per hour of operation. Yeah. So. Yeah, I know it's gallons per hour. It doesn't matter if you're driving it or it's idling. It's just burning and stuff. So something like Hummer. You know, you have the Hummer 3, like $20 of gas like that. Oh, just read it once.
Oh my god. Professor, so you say a Rogers MA is an MBA and up? So what's a B? Like 70 and up?
Something, I don't know. So what is our U in this case? X to the 9th. And the du is 9x to the 8th dx. So I need a 9 and a 1 over 9 in front. So 1 over 9 integral. All of the green stuff is the du. So we have sine of u. Yeah, sometimes it can be fixed. Sine of u du. Right? So now that is going to be 1 over 9. Integral of sine is yeah, negative cosine u plus c. I don't care about u, care about the x. So cosine x to the 9 plus c. Do we all have this? Or in the vicinity at least, so we can get it better over time. All right, the integral of ln to the 63rd degree x divided by x dx. What is u?
1.
Very good. U is ln x. And what is du? 1 over x dx. Good. All right, let's see. So the 1 over x dx is du, so I have u to 63 du, which is u to 64 over 64 plus c, and that will be ln 64 of x plus c. If the notation is driving you crazy, you should know that when you write sine squared x, it means sine x everything squared. So the same thing for ln squared x is going to be ln x everything squared. These are all different than sine x squared and different than ln x squared. Those are different things. So just notation wise. Yes.
So the ln 64x, is it going to be divided by 64 in the denominator?
Yes. It's clearly divided by 64. If you look at it, you see right there. There's a 64 right there. 64. I know. I'll still show up next week. All right. Let's take a look at some problems from the textbook, since you became expert on U-subs so quickly. We never discussed any of the square root problems, which is a shame, but luckily textbook has plenty of square root problems for us to work on, so let's start with some of the favorites. 2x squared divided by the square root of 1 minus 4x cubed dx. Do we see function derivative pair here? What would be the function? What would be the derivative?
The x part should be
Yeah, x cubed and x squared. Does square root have any pairs with it? No. So square root must remain in substitution, right? In substitution integral, square root will remain, and your u's will be focused around the cube, and the square should go away with the du. Now let's see. Give it the best shot.
Why does that always come up? It's like the second time.
No, because the hot topic is really different. This is science. So crazy.
Can you just tell me what a U is? 1 minus 4x cubed, the whole thing. Because we know how to deal with the square root of u, we don't know how to deal with the square root of 1 minus 4u or something like that. So the entire thing under the square root is u, and then we have to deal with the fallout with minus signs and everything else that happens.
This lab I 1 month ago. Yeah, I forgot. This one. We're talking about this. Yeah, that's what we did.
Okay, so I need negative 12x squared. I have 2x squared. That means negative 6 and negative 1 over 6 to balance it. So now negative 6 2x squared is going to create negative 12x squared, which I need. So what is this now? It's negative 1 over 6 integral of 1 over square root of u du. This entire peanut over here is du. Yes.
Can you skip that step?
What step?
The step where you put the -6 and the 1/6 in the equation with x.
Well, you have two options. Your option is to work with what you have by dividing here by -6 and by -6 to create this to replace, or to add in multiply by -6 and 1/6 to create this, because they have to match. Clearly they don't match, because one is -12 and the other one is 2. So they don't match. So you have to fix them one way or another. That's why I said you pick your favorite way to fix. Which one you like better?
Well, when I did it, I got the same answer. I just didn't do that step.
What did you do? Oh. Keep
So
thinking.
Somewhere in your head you did it.
So yeah, so keep thinking. So this is now -1/6 integral of u to the -1/2 du. So that's -1/6 u to the +1/2 divided by 1/2 plus c, which is -1/6 times 2/1 times square root of u plus c, which is -1/3 square root of u plus c, which is the final answer, -1/3 square root of 1 minus 4x cubed plus c. And that's the final answer. Bueno? All right, next example. Crank the heat up. Integral, open parentheses, square root of x plus 1, everything raised to the 4th, divided by 2 root x dx. So what is the function that doesn't have its pair? I like to start there. We see the square root, we see hopefully x to the fourth, we see another square root. Which function doesn't have its pair in terms of the derivative? X to the fourth. So that has to survive. So now let's make the whole thing that it's to the fourth, u to the fourth. So there is a logic, right? A logical way of thinking to get there. And uses the function derivative pair. So you have a square root of x whose derivative is 1 over 2 root x. Ooh, I see that. And then there is also x to the fourth, which I don't have x cubed for. So make this u cubed, but then immediately that tells you that this is u. And you have the du spelled out. So this is actually, in comparison to some other problems we did, really straightforward problem. You might didn't see it, but that's okay. I mean, you're getting there. Especially if you don't have memorized that the derivative of root x is 1 over 2 root x. Then sure, we have issues. So this is just u to the 4 du. Look, this is beautiful, right? The whole crazy, insane thing up there compresses into u to the 4. So we have square root of x plus 1, everything raised to the 5th power, plus c, and problem solved.
So I guess what I'm having trouble seeing is anytime you have whatever you made du, even if you have it 3 times up there, it all condenses into the 1 du?
Yes, because it says clearly that du is equal to the whole thing. Right? So the whole thing is du. It's a replace, it's substitution, right? So if you want to think about it, all of this crazy expression condenses into it. Yeah, it's like a book bag, right? You put 15 things in the book bag and just drag it around, right? So, yes?
Yeah, you can see.
Oh, there's a 1/5. There's a smile. Okay, good. Approved. All right. We're about halfway through the lecture. There are, well, this is just the method of U-substitution, but then there are definite integrals where you have to transform the limits, and also there is some modification on it, which is called back substitution. Remember how there's a part 2? So if you want to take a break, then we can go do part 2, and then we'll do part 3 next time as a review. Take a break? All right, and then we'll restart the stream. Same lecture, part 2.